I'm going back to you. And what did I do? I thought about you. Thought about you. Embrace me, my sweet embrace. Embrace me, my airplane. So just to look at you, my heart grows in me. You and you alone bring out the gypsy.
Okay, let's see. Sarah B, Claire, Matt, Luke, Jaden, Emma, Liza, Stuart, Ethan, Manya, Olivia, Kashal, Diego, Darwin, Sean, Jules, Doa, Matthew, Colin, yep, Emily, Rennick, Sarah T, McKenna, and Sarah B, right? Okay, anybody I missed so far? No. Man, where is everybody today? Must be a slow bus or something. There we go. Okay, Rennick, is that right?
Yes.
And Olivia? Okay. Help me out. Matthew. Good. Gotcha. Doa, is that right? Okay. 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 All right, time to get started. So here's what we were doing last time. We were talking about double integrals. Of course, we spent a bunch of time so far on double integrals, but now we're looking at where it gets kind of geometrically more interesting, and that is, what if your domain is not a rectangle? So you have a domain kind of like this, something kind of like that. Okay. So punchline is you can slice it up the same way. It's no problem. You can still do a chop it up, add it up kind of approach to things. And really the only difference is that as these slices move along, the points that are the end points of the the x integral, the inside integral, more to the point, well, they move, right? Depending on where y is, those points kind of follow that curve. Entirely determined, of course, by what the domain is. And so we don't even need to draw the three-dimensional picture, right? We can just look at the domain itself and see how, as y moves, these points move, they move along these curves, and where those points are, oh, let me switch colors, at where those points are, determines your bounds. So my little shortcut memory trick, connect the dots, as it were, between these various objects is, if you're interested in bounds, identify the relevant point. That point, identify the relevant curve that it's moving along. That curve will have some equation, solve it for, of course, the variable that you're interested in. Okay, and we did some examples last time, so real quick, this example here, let's see, we have x going from 0 to 1, for which a slice looks like this, right? And then the y bounds, if you want to know what's the range of values for y, well, y is going to start, well, wherever that point is and end wherever that point is. And those points, let's see here, respectively, are on, well, the lower point is on that curve, which has this equation. We're looking for a y bound, and so we solve for y, and we get 0. The point here giving us the upper bound is on this curve, which has that equation. Again, we're looking for a y bound. So we solve for y. Again, lucky break happens to be easy here in this case. Isn't that nice? You won't always get that lucky, but solve for y, and that's your upper bound. Right? Is everybody good with that? Things change a little bit, you'll notice, when we slice the other way. Not dramatically, but they do change a little bit. And let me just go to the sort of the punchline, and that is, you will notice that these bounds, let's see if I can get these on the page at the same time. These bounds and those bounds, right, do not follow this rule, right? So remember, with rectangles, you can just do this. It doesn't really matter what order you slice. You can put the inside outside, the outside inside, just move the bounds along with it. It's fine. Absolutely not for anything other than a rectangle. You just have to go through the slicing process again. Okay. All right. All right, and this is getting close to where we left off last time. We talked about the meaning of this phrase, bounded by, and then I realized I was out of time. So remember, bounded by means that the curves listed are, make up the boundary of the region in question, but furthermore, that the region itself is actually bounded. And so it can't be, this phrase bounded by will never be used to refer to a domain that, extends infinitely in some direction or something like that. Okay, so this domain D is this right here. Okay, everybody good? Okay, so let's start slicing it up, and let's see here. We're going to do this both different ways. You'll see, and we'll do them one at a time. Let's start with doing our X slicing on the outside. X goes from -2 to 2. How did I know that? Where did this come from? Well, arguably, we're kind of following the pattern. This lower bound of -2, for example, the bound comes from that point. That point is on, well, it's actually on two curves. It's on this curve that has that equation, and it's on this curve that has that equation. So the point I'm interested in, I have two curves and correspondingly two equations. And so in here, I need to solve for, by the way, don't forget, don't lose track of what you're trying to solve for. And very often I, in fact, lose track and then have to consciously remind myself, I'm trying to find my lower bound for X. This is, and finding the bounds for the x integral. So in these equations, I need to solve for x. If you kind of lose track, you might be tempted to say, oh, cool, y equals 4. And then you you put 4 there. And of course, that's wildly wrong. Okay, so don't lose track of what you're trying to solve for here. We're looking for x bounds. So we solve for x. And by the way, we of course do get 2 candidates. We get 2 and -2 in solving for x here. How do I know which one it is? Do you just pick based on, do you flip a coin? Of course not. Sometimes you have to look back at the picture for additional cues, right? Excuse me. And the additional cue here is that this bound that I'm looking for, this point defining this bound, is clearly negative. Right? It just is. I mean, I'm looking for that lower bound. So yeah, it's on the one curve. Yeah, it's on the other curve. But yeah, further, it is also clearly a negative x coordinate. And that's what tells me it has to be -2. Everybody good? Okay. So very similar analysis goes into finding the upper bound. You know, how do I find that upper bound? Well, it's that upper bound is defined by that point, which is on these 2 curves, which have these same 2 equations. This time, though, the additional information, this one's clearly positive. So I have to pick the positive, and that gives me +2. Okay. Let me pause, give somebody a chance to ask a question. Okay. All right, so now let's do it the other way. Let's do the y slicing on the outside here. Excuse me. So y. So wait a second. I didn't finish the first one. Sorry, got ahead of myself. We did our x bounds. X went from -2 to 2, and then we fix a value of x. For that value of x, we got to do our y bounds. Silly me. And there's what our slice looks like. Y starts that point, which is on that curve, which has this equation. Wait a minute, I've already lost track. What am I solving for here again? I'm solving for y. So within this equation here, I need to solve for y. Lucky break. It's already solved for, and there's my lower bound. And then same process for the upper bound. My upper y bound is defined by that point, which is on this curve, which has that equation. Again, reminder, I'm solving for y. So in this equation, I need to solve for y. Again, it's already solved for. I keep getting lucky. Isn't that nice? And upper bound is 4. Yes?
So if you were like trying to picture this, is there a reason you have to pick 4 as the top bound and x as the lower bound?
Yeah, absolutely. Because so we are going so we're, y is going that way, right? And so, keep in mind when an integral is a Riemann sum. A Riemann sum is limit summation f of xi, delta x. Well, this is 2-dimensional, so delta x, delta y. Those deltas are, b minus a over n, or d minus c over n, depending on which variable we're talking about, right? If you get the bounds backwards, then your deltas are going to be negative instead of positive. And we want to talk about area, right? So in order to make sure that you actually get an area, you got to make sure that you go lower to upper. Absolutely. Does that make sense?
Yeah.
Cool. Great question. Anybody else? Okay, so slicing the other way now. Same region, same 2 curves. Doing our y slicing first. Well, we start there, we end there, right, in our y slicing process. And this lower point, I'm going to say, is it's kind of a freebie, right? It's the origin. The upper one is it's clearly on that curve which has that equation, which I am looking indeed for a y bound, and y is therefore 4. Nothing to it there. Now being careful looking at the x bounds, x starts at that point, ends at that point. Both the starting and ending values are on the same curve with the same equation. Right? Now, again, let's be careful about this. Don't forget, you're looking here for x bounds. We already know the y bounds. So we have to solve for x in this equation. A lot of students mess up and correctly identify the point and the curve and the equation, and then they just write down x squared in there because that's the curve that it's on. It's on the x squared curve. Right? Well, that doesn't make any sense. You can't have x, for one thing, as a bound for the x integral. So it's implausible to start. But it's also not the process, right? So we're looking for x as a function of y. In order to get that, you have to solve for x. So don't forget to solve for x. And in doing so, you notice that again, you get two different options in solving for x. And well, the lower bound is clearly negative. So the negative one is the lower bound. And the upper bound is clearly positive. So the positive one is the upper bound. Everybody good? Okay. All right. Okay, so sometimes you get lucky, sometimes you don't. Again, here, in solving for y, conveniently, those y's were already solved for, and that's nice, but you can't count on that, right? You have to make a conscious effort to, in your mind, consciously recognize, wait a minute, which is the variable I need to solve for, and then actually do that when necessary. All right, now let's look at these two different options of iterated integrals. Which one do we like better? I don't know if y'all have a preference. I like this one better, right? Because I don't like square roots. I don't know. I'm scared of what's going to happen. And of course, I don't know what this f is here, right? But I'm concerned about the possibility that when I take these values of x and plug them into the antiderivative, I'm scared that my y integral is going to have, oh my gosh, it's going to have a lot of square roots in it. That's liable to be ugly. I don't even know if I can do that. Depends on what f is, of course. Okay, so you could, if you want, just kind of always write down both of these options and then just kind of look at them and decide which one looks nicer, right? You can't, and sometimes you kind of have to do that. But there is a tip off. You can kind of trace back in some sense, where did this ugliness come from, and try to anticipate in advance which one's probably going to be the nicer approach. And I argue as follows: where did these these x bounds that have the ugliness in them, where did they come from? They came from the fact that I had to solve for x in this equation. Why did I have to solve for x in that equation? Because x is on the inside. Right? So I suggest you look at your algebra that you're given and ask yourself, which variable do you prefer to solve for? Would you rather solve for y, or would you rather solve for x? Don't worry about the details yet, right? Just looking at the givens. I'd rather solve for y in this case. Not that I can't solve for x, but I'd rather solve for y. And because I would rather solve for y, I'm going to put y on the inside. Everybody see my reasoning there? So I think this is a very nice trick. I'm not going to say this will always help you make the right choice, but it's really, really high odds. This is well worth this point of view to sort of think that through before you make your decisions. Okay, and there are other considerations, but nevertheless, yes.
The zero on the lower bound for the second picture.
Yeah.
Is there a way to get that without the picture? Did you like that?
Oh, that's a good question. Maybe. I rely hugely on pictures. And I do remember that way back when in my physics days, had to do an integral. It was a 6-dimensional integral. And so I couldn't draw a picture, and it was brutal, right? Absolutely brutal. So I don't know, maybe my reliance on pictures comes from that experience. I don't know. But so sometimes, yeah, you can make algebraic arguments, but it's no fun. And it's hard to trust yourself that your algebra has been done correctly, right? I suggest that the by far best way to do this is to realize that we're looking for y bounds here, right? And so there's my lower and there's my upper, and let's talk about the lower. And what do I know about that point? Well, look, if you want to really get precise about it, you could say, well, that's clearly the minimum value of that function, and then just think single variable calculus and do it like that. So that'd be if you want to have a process to follow, I think that would be in this case. The problem is identifying that this is the curve that it was on came from the picture. So yeah, I'm a big fan of the picture. Yeah, is that satisfying?
Yeah.
Okay. Okie dokie, moving along. Here's another one I'm going to do 2 different ways. We got a triangle, certain corners. So there's our domain. And again, we have a some double integral. Notice, by the way, I'm focusing on what I like to call the phase 2 part of the problem. I don't want to worry for the moment. Let's see, where is my, here we go. I don't want to worry for the moment about, what application are we addressing? Why am I computing a certain double integral? I don't know, whatever. And I don't want to focus on actually computing the resulting iterated integral. Y'all know how to do that, right? For the moment, for these examples with non-rectangular domains, I'm focusing on this part of turning a double integral, don't worry about where it came from, into an iterated integral. Don't bother computing it. Let's just focus on this conversion process. Again, phase 2 of our 3-step strategy. Okay. All right. Okay. So again, let's slice it up, starting with y, which goes from, you might say, from 0 to 1. All right. So the y bounds, no big deal. Right there in the picture. Then for a given value of y, x goes from, let's see, that point, which is on that curve, which we're going to have to do a little bit of algebra here, apparently, to find what that equation is. You write down that equation, you solve for y, solve for x. See, look how easy it is to get it wrong. Solve for x. Because you're looking for an x bound here, and you will get that x is y, because that's the line y equals. And then the upper bound, right? That point for the upper bound is on that curve, which has an equation you can again solve for. Don't forget, we're trying to find an x bound. We're solving for x, and you get that. Goes through just fine. Is everybody happy with that one? All right, now let's do it the other way. Doing our x slicing first. Well, no problem. X starts there and ends there. X goes from 0 to 2, which you'll notice does not show up in what I have written on the right, but at a glance, you would say x goes from 0 to 2. Let me show you what goes wrong if we try to proceed with x going from 0 to 2. If we simultaneously try to consider all of these values of x between 0 and 2, let's think about our y bounds. And the good news for our y bounds is all of the lower bounds are on that curve, which has that equation, and that's fine. The bad news, though, is that my upper bounds, keep in mind my x slices look like this, right? My upper bounds for y are sometimes on that curve, sometimes on that curve. Which curve do I use? Which curve? With what equation? There's two equations here. For some values of X, you have one equation. For other values of X, you have different equation. And so there is no single thing that you can put there as the upper bound for Y. So you can't write, even though X ranges from 0 to 2, you can't write down an integral that way. And so it's really annoying and uncomfortable. So what we have to do then is we have to recognize that, well, we're going to have two separate integrals. On the one hand, we're going to have X going from 0 to 1. We'll look at those values of X. And for those values of X, Y, the upper bound, is on that curve. That's for all of these values of X. Now keep in mind, X going just from 0 to 1. And that curve with that equation, solve for Y, and bam, no problem, fine. But then for these values of X between 1 and 2, different story, as we previously noted. For these different values of X, the upper bound on my, again, I have these Y slices, right? The upper bounds are always on that curve, which has different equations. Solve for Y, again, don't forget. Solving for Y, and you get that. Now, both of these individual integrals work out fine. There's no problem, but there are two of them, right? So again, given your choice, if you were going to try to compute this integral, and if you were going to choose between that or this, right? Give me that one. That's half as much effort on my part, ballpark, probably. Who knows? Depends on F, but probably about half as much. The expected effort, probably about half. Okay. All right. Now, so again, an approach you can take to making sure that you end up with the easiest one is slice them both ways. Look and see what you got, right? But I'd rather try to anticipate, and here's the way I anticipate it. As I am doing X slices, notice I sliced through a corner. Sliced right through that corner there. Right in the middle of my range of values of X. The reason that the corner matters is because the corner is where these two curves intersect. The reason it matters that those two curves intersect is because that means that's where my upper Y bound, right, sort of jumped from the one curve to the other curve. And the fact that my upper bound jumped from one curve to the other curve is why I have the summation of two separate integrals in the first place. So my sort of tracing it back to ultimately what's the giveaway that this was a bad choice, that this order of the slicing, was a bad choice. I think the giveaway is that X slicing has you slicing through a corner. So my rule is try not to slice through corners. I think it's a nice, simple, geometrically easy to capitalize on rule that will, again, not always, and there are rare exceptions, but very often will point you in the right direction. Try not to slice through corners if you can. Everybody good? Okay. All right. Yeah. By the way, of course, I also technically, arguably, kind of sliced through a corner at the beginning there, and also then at the end here. But the thing is, I was going to start a new integral there anyway, and when I get to the end, well, I was going to end the integral there anyway. So at the beginning, at the end, it doesn't matter. Don't worry about that. Of course, you're always, in some sense, going to kind of, well, you're very often going to have corners at the start and the end, and that's not a problem. Yes.
So that's why on the top one, the corner up top doesn't matter.
Correct. That's right. Yeah. So what matters here is that as I did my Y slicing, sure, there's corners in my start. Sure, there's a corner at the end, but in the middle, where the meat happens, no corners. Yeah, exactly. Everybody happy? All right. Sometimes the domain is not given. Sometimes you have to actually do a little bit of work to figure out what the domain even is. So, all right. So in particular, I suppose I want to find the amount of volume that is, let's see, I'll do this. Yeah, the volume that's between two given surfaces, and you can plot those surfaces, and here's the volume that's in between. And how am I going to compute that volume? Well, I'm going to look at the shadow down here, and I'm going to argue that if I were to look at little pieces of area down here, little pieces of area down there, over each piece of area, I could look at the height here, which is the difference of those two z coordinates. And I could then say, okay, well, height times the area of the base gives me volume. And let's see here. Yeah, so the amount of the volume of that French fry, the thing, of course, I want to add up all the volumes of those French fries, is this expression here. And it kind of looks like I have a double integral and we're ready to run. Problem is, I don't know what my domain is. My domain isn't given. Right? Everybody see the problem? By the way, a lot of students are uncomfortable with this as, being a volume, but we're computing it with a double integral. So that's where the, it's important to think through the Riemann sum aspect of this, right? So in other words, for each piece of this area, I'm doing a calculation. The fact that that calculation is geometrically about things that are somewhere else isn't the point. The point is that it's for each little piece of this area that I'm doing a calculation and adding things up. And so this is therefore what my domain is. Okay. All right. So, all right. How do I figure out my domain? Again, it's not given. This again, the picture, indispensable. I don't know if I'd be able to do this without pictures either drawn or imagined in my mind, but you kind of see the geometry of it. This is an unavoidably geometric class, right? I'll go ahead and take this as an opportunity to remind y'all. I've already made the pitch, but if you're good at drawing, super. If you're not, this is the time to get good at drawing, and it's a skill. Knowing the tricks of the process can be extremely helpful, and of course, it also takes a lot of practice. So I can't make you practice, but I can tell you the tricks. And so I have a video, two videos, in fact, on the YouTube channel that are all about everything that I know, all the little tricks and shortcuts and things like that I use to make decent 3D drawings. And so if you want to know everything that I know about how to draw mathematical figures, give a look to that YouTube video. Okay, and I'm sure that there's many other videos out there as well. Okay, so where does this domain come from? Well, I would understand this domain by this boundary curve. Where does that boundary curve come from? Well, it's the shadow. I mean, again, appeal to the picture. It's just the shadow or the projection of that curve. And that's just purely geometric appeal. Where does that curve come from? That curve is where this surface intersects this surface. Right? So what I'm going to want to do in order to find the boundary of my domain, which comes from this sort of edge of the, whatever that shape is where these two surfaces intersect, and therefore it's what I get when I solve with both of these equations. I get both because the intersection curve is on both surfaces, and therefore both equations apply. Everybody good? All right, now here's where a lot of students mess up. A lot of students say, oh, okay, I've got both of these equations, so I'll set these equations equal to each other, and off we go. And let me just make sure everybody's clear. That's not a thing. It makes no sense at all to set equations equal to each other. It's absolute nonsense, right? What? I mean, 2 equals 2, right? 3 equals 3. If I want those to be true, can I set 2 equal to 3? No, of course not, because that's absolute nonsense, right? So it doesn't make any sense to set equation, but I'll see this all the time where students will be like, I don't know, I guess that I'll set that equal to that and solve. It doesn't make any sense. Everybody see why that's bad? Okay, so what you need to do is think through, what are you actually interested in, and what does that tell you to do algebraically? So what we want here are, we want to know values of x and y, certain key values of x and y. Specifically, I want to know the values of x and y where, let's see, I want to know these values of x and y where the height up to there and the height up to here are the same, right? I want those 2 heights to be the same, because that's, when those 2 heights are the same, that's where the surfaces intersect. Or said differently, I want to know where this z is equal to that z. I want the z's to be equal. So don't set the one equation equal to another equation. That's nonsense. But you realize you can solve for z in both of these equations, and you want those 2 z's to be the same. That comes straight out of the diagram. Everybody okay there? Okay, so no big deal to do that. Solve for z in both of these equations. The first z came pre-solved for. Again, sometimes you get lucky. The second z was not. You have to do a little bit of algebra to solve for that second z. No big deal, but you do have to do it. These are the things you set equal to each other then. And then you do some completing the square, do the appropriate algebra, and it comes down to that equation right there. And it's kind of interesting how it turns out that son of a gun, look at that, it's a circle. A parabola intersecting a plane gives you a circle. Gives you a projection, I should say, that is a circle. How we doing? Everybody good? Everybody remember how to complete the square? This process here. I think certainly when I was in high school, it was underappreciated. Anyway, I hope everybody's good with that. Okay. Okay, moving along. So we just finished 5.2. We move on to 5.3. This is the shortest section. Oh my God, I don't even know why this is a section. It's like there's really one example that's, and everything else is kind of this. It's same. So I have 1 page of lecture notes in here. I'm just going to show you the one key example. And to me, this should have been a subsection of 5.2, but whatever. Sometimes when you're given an iterated integral that you wrote down, perhaps in good faith, seems like the reasonable way to do it, or that maybe that somebody came to you with this a pre-iterated integral, right? It's actually better to switch the differentials. So that happens sometimes. And so this is actually a really good example, because if you look at this inside integral here, you're out of luck on this inside integral, right? There is, if you ask what is the antiderivative of e to the x squared, you can't write it down in what we call closed form. You can write it with power series, Taylor series, that kind of thing. But then when you take the antiderivative, then your antiderivative is a infinite series, and that's right. Okay, so if you try to compute this iterated integral brute force, you hit a wall. Okay, so what we're going to do is change the order of the differentials, change the order of the slicing. And what I'm going to do is kind of reverse engineer from these bounds corresponding to these differentials. From those bounds, I'm going to try to reverse engineer what is the domain for the original double integral that this came from. Not given, but I'm going to try to find it. So, okay, well, let's see here. Apparently y goes from 0 to 1. All right. So my domain is in between there, right? There's a bunch of slices in here and they started at 0, they ended at 1. So, well, I guess my domain must be in between 0 and 1. Yeah. Okay. All right, next, x, the lower bound for x is y. Said differently, the lower bound point is on the curve x equals y. Oh, you know what? Let me recopy. My y bounds 0 to 1. My lower bound for x is y. I need to do like, there we go. Get it all on the same page. So lower bound for x is y. That gives me that curve. My upper bound for x is 1. So straight out of the integral, the iterated integral you're given, you can just figure out what the bounds are and therefore what the original shape is. So my original domain must be this triangle, because that's what's between these values of y and on any slice of which then goes from the correct lower bound to the correct upper bound. Everybody happy with that? Okay. All right, so I know what my double integral is. Now I want to actually slice the other way, see what my other sort of iterated integral option is. And so now I'm going to slice x on the outside. X goes from 0 to 1. Yeah. And then for any given value of x, y starts there, which, okay, is y equals 0. And it ends there, which is on this curve with equation, with equation x equals y. I'm looking for y bounds. So we solve for y in that equation, which is not much trouble, and it's x. Okay, so we reverse engineered the original domain, then we re-sliced and have effectively switched the order of the integration. Notice we started with dx dy. We have ended with dy dx. And now you can look at this integral and say, well, yeah, but you've got all the same problems because you still have e to the x squared in there, and we still don't know how to take an antiderivative of e to the x squared. Not true. We don't know how to take the antiderivative of e to the x squared with respect to x. With respect to y is easy, right? Because y being a variable means x is a constant, means all this e to the x squared is a constant. And it's super easy to anti-differentiate that with respect to y, and then plug in these values of y, and you get this as that entire integral. Nothing to it. Okay, but now there's that looming e to the x squared did not disappear. We still have to do an antiderivative with respect to x. So why is this any better? Well, it's better because this gave me that factor of x, and that's what allows me to do a substitution, u equals x squared, and then this is going to be my du. Well, there's a 2 in there somewhere, right? But I mean, but you can see it's all, you can see daylight at this point, and it's all over. Everybody good? Yes.
Would you mind just doing the use substitution real quick? I'm like a little rusty. on it.
Okay, so that's definitely something, I think that's actually a perfect office hours question. Well, let's talk about that in office hours. But yeah, so this is a good opportunity to remind everybody that Calc 2 is prerequisite of this course. I'm going to assume that you're strong with, I'm going to say pretty much all of the integration methods, so integration by parts, use substitutions are the two big ones. But there are, don't forget, trig integrals and half angle formulas and stuff like that. Trig substitutions, I'm a big believer in and have a YouTube video about. So if you are a little rusty, and a lot of students are, so no problem, right? But if you're maybe a little bit rusty, then definitely want to sharpen up those, polish those skills up as soon as possible. Yeah. Oh, I will say though, in a lot of Calc 2 classes, they will kind of, they'll go somewhat deep into, sometimes they'll talk about, hyperbolic integrals, hyperbolic trig functions. Don't worry about that. But the standard stuff, I think, is all really important. Okay. So so that, again, the world's shortest section. We're now done with 5.3. Okay, moving along. 5.4 triple integrals. So let's take stock for a moment. Y'all had an entire course on single variable integrals, Riemann sums, such. And now we extended that to double integrals. The idea of a double integral is that instead of having a domain that was an interval, we take a domain that's a two-dimensional region, right? And we had to kind of reinterpret, but there's what remains with single variable integrals and double integrals is chop it up, add it up, right? The big strategy of chop it up into little pieces. You have to chop twice if it's a two-dimensional thing, right? But still chop up your domain into little pieces. And then on those little pieces, the problem is simpler. And then add up your answers for all those little pieces. So that's all a Riemann sum is. That's what we sort of translate over to the two-dimensional case. And what we're now going to do is simply do that, chop it up, add it up on a three-dimensional region. So conceptually, it's not that different. I should say strategically, it's not that different. Chop it up, add it up. Well, some details are going to be different. When you have a three-dimensional thing, you have to chop three different directions instead of two, and there's an extra variable to deal with. And so, yeah, it's going to look different. Geometrically, it looks different, but strategically, it's kind of the same. So let's dive in. So when would you need to add up over a three-dimensional region? Well, what if you're computing the amount of mass in a three-dimensional solid, where density depends on not just X and Y, but also depends on Z2. Double integral won't do that. Double integral will assume that density is a function of just the two variables, X and Y. That Z dependence, it just doesn't work. And then there's a million other examples, just as a for example. And if y'all haven't seen more than one dimensional probability density functions, or if you haven't had any statistics or probability before and don't know what probability density function is, don't worry about it. But it's another thing which can be three-dimensional, and which you very reasonably might want to add up over some space. Okay. All right. So here's the process. Here's a three-dimensional. So this is not an interval. It's not a rectangle. It's a rectangular box. It's a three-dimensional, kind of a three-dimensional rectangle, if you will. Okay. Maybe there's a bunch of mass. I want to compute the amount of mass in there. Maybe it's a fish tank, and there's sediment kind of floating around. I want to compute the total amount of sediment or whatever, bacteria, population, whatever. Well, I need to slice. And so I'm going to slice that way. And then I end up with, of course, a bunch of pieces that are really too big to work with. Right, those pieces are too big. So I'm going to slice then again. I'm going to slice, oh, whoops, sorry. Like this. And now I have smaller pieces having sliced that second time, but again, these pieces are still kind of big. They're long anyway, right? So I have to slice a third way. Etc. And I think you can see again geometric appeal if you have a solid, if you slice it in each of the three different ways, then what you end up with is a bunch of little bitty boxes, a bunch of little boxes that look, something like that, for example. And that is a little piece. And I could say, for example, that, what's the total amount of mass in this great big thing? Well, that I don't know, but on this little piece, I mean, it's a little, the density is approximately constant on that piece. Pretty close, in the limit, that round off error is going to go away. And on that little piece, mass, it's just density times volume. Nothing to it. Okay. All right, notice in that slicing process, I effectively have to slice up, A to B on the x-axis, and we already wrote down those formulas, no problem. I also have to slice up this interval from, you could call it C to D. On the y-axis, again, we already know how to do that. That's the exact same formulas that we already developed from double integrals. What's new is that when I'm doing vertical, I guess you'd call this horizontal, well, anyway. When you're slicing like this, right, then you are effectively slicing up the z-axis, and same pattern, right? Instead of slicing up from A to B or C to D, now it's from E to F. And so the original length of F minus E, we chop it up into N pieces, therefore of size F minus E over N. And each one is one delta Z further above the previous one. So morally equivalent formulas, highly analogous anyway. And all of that, again, a bunch of details that we need to write down for thoroughness, but we're basically never going to use. What we're actually going to do is just say, this is what we mean when we say, chop it up, add it up on a box. We mean this. This is chop it up, add it up on a box. And we're going to be doing a lot of this. We're going to be computing masses and probabilities and populations, blah, 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 on solid boxes. And so we need a terminology. We're going to call it a triple integral. And we need a notation, which is this right here. Again, I emphasize, I strongly encourage that you think of these as just conveniences. What they refer to are the Riemann sum. So anytime you see the word triple integral, you should think Riemann sum. And anytime you see this notation, you should think Riemann sum. Okay. Everybody with me so far? Okay. Oh, and I am out of time. Again, just like with double integrals, you're not responsible for all the business about irregular partitions and test points. It's not relevant to what we do in this class. And we'll draw the line right there. Y'all have a good day. See you later. Yep, sure thing. And office hours in 9 minutes.